Section 7.6 is on improper integrals. We're going to split this into 2 days. Day 1, we're going to learn about type 1 improper integrals. An improper integral is an integral taken over an interval which is infinite, or the function has an infinite discontinuity. So we begin with this example, y equals 1 over x squared. We have the graph here, y equals 1 over x squared. Let's start at 1 and talk about finding area under the curve as you go to the right. So it might seem a little impossible to take area of a curve that doesn't end. The curve gets closer and closer and closer to the x-axis, but there's always space between the x-axis and the curve. It seems like that area would just add up to infinity because you just keep adding area forever. Let's take a closer look. If I start my interval at 1 and then I picked a point down the line, let's call it t. Let's find the area from 1 to t, and then we're going to imagine t moving over as we go. The area of the region under the curve is the integral from 1 to t of 1 over x squared dx. The antiderivative for that is negative 1 over x, and we evaluate from 1 to t, which gives us negative 1 over t minus a negative 1. So that is like a positive 1. So we actually get 1 minus 1 over t. So what I want to do is take that value for area, okay? That's our area expression. And now imagine t moving down the line. So what I'm going to do is I'm going to take the limit as t goes to infinity on this area. So that means I'm taking the limit as t goes to infinity on the expression 1 minus 1 over t. Now, this is the spot where I do not want you to substitute infinity in for t. Do not literally put that infinity in for t. The first number is 1 minus the value of that fraction as t goes to infinity will be 0. Actually, area under that curve from 1 to infinity is approaching 1 as t is approaching infinity. The correct notation for this: the integral from 1 to infinity of 1 over x squared dx has to be rewritten as the limit of the integral. So take t to infinity and represent the upper limit as t when you do that. So there's going to be 2 steps every time when you work out an improper integral. First, you're going to find the integral, then you're going to take the limit. Our book gives us advice. We have a definition with some more information. The definition for type 1 is the type of integral where infinity is occurring as at one of the endpoints of the interval. So in part A, we're going from some value of a up to infinity. So you're going to have to rewrite the integral as a limit. This notation has to be in your work. The other version of type 1 is where our integral is going to negative infinity. So that would be at the start of the interval, and we'll represent the start of the interval's limit as t, and this limit notation has to be there. Notice how we have 2 terms. There's a term for an improper integral that ends up having a value, and that is convergent. Example up above was convergent because we found the integral to be equal to a finite number. If we ended up getting infinity, then the integral would be considered divergent. It is possible that our integral could have a lower limit of negative infinity and an upper limit of positive infinity. If that occurs, we can split the integral up into 2 integrals. We'll find some value, usually 0, to work with, and we'll set up the integrals for each. We'll have a limit for negative infinity as our lower limit, and we'll have a limit on this integral where infinity is our upper limit. As long as these 2 integrals are convergent, we're allowed to set this up. More information about this, another reminder that infinity is just a symbol, it's not a number. So do not put it into your work as if you're substituting it in. Rather, you need to analyze your expressions and put the proper equivalents there for them. And remember, this is a two-step process. We're going to evaluate and simplify the integral first. Then remember, you're going to have to evaluate the limit and therefore show the steps in your work. And as long as your function is positive, you can think about the improper integrals being interpreted as area. So if that helps you along the way, you could talk about those as area. Okay, we'll look at another very, very important example. Here's the integral of 1 over x, and we're going to go from 1 to infinity. Let's determine if it's convergent or divergent. Proper notation is going to be checked. Proper notation is going to be checked. Here's the original math problem. We need to set up a limit as soon as we know we're dealing with infinity. I choose to keep using the variable t in my notation. Other textbooks might use other letters. T is taking that place up as my upper limit. And now that my limit is set up, I'll turn my attention to finding an antiderivative. Keep the limit notation in your work. Don't leave it out as you work out steps to your integral. The antiderivative will be the natural log of absolute x. Again, keep that limit in every step of your work. I'm going to evaluate the function now at the limits. Getting ready for the limit now. I know that the natural log of 1 is 0, so this is just natural log of absolute t. I just want to remind you for a moment what that looks like on a graph, the natural log of t. The natural log function passes through the x-axis at 1, 0. It is increasing and concave down all the time. And if you move to the left, it is respecting the vertical asymptote it has at x equals 0. So when you think about it, you're thinking about t going to infinity. This function is forever increasing as it goes to the right. So when I evaluate, this is me analyzing, I'm taking the limit now. The natural log of a very large number is going to be a very large number. So this answer is infinity, and that means the limit does not exist as a finite number. Therefore, the integral is divergent. There's an important thing to notice. The first integral we looked at the start of the notes was the integral of 1 over x squared. It actually equals 1, and that means it converges. However, the integral of 1 over x does not converge. It diverges. So something is happening there. We know that as x gets larger and larger and larger, both of these fractions approach 0. 1 over x squared approaches 0, and 1 over x approaches 0, as x gets bigger and bigger and bigger. But the reason why the integral from 1 to infinity of 1 over x squared equals 1 is because that fraction approaches 0 much faster than the other one. We have a theorem to follow when we get integrals of this nature. We get a 1 to infinity. It could be 2 to infinity or 3 to infinity. 1 over x to a power. So I'm going to write 1 over x to the p for power. If you get integrals that look like this, and you'll get a lot of them. This is convergent if p is greater than 1. It is divergent if p is less than or equal to 1. We're going to use this a lot in the upcoming chapters. So this is a very helpful theorem to have. If the power is greater than 1, we know we have a convergent integral. If the power is less than or equal to 1, we know we have a divergent integral. So it's a very good rule. It's easy to follow. Let's look at one more example. This is number 16 from our book. Number 16 has obviously limits that are infinity. With the infinite limits on both sides, I'm going to have to break this up into two integrals. I'm going to start with using the variable a. As a goes to negative infinity, for the integral from a to 0, of x times e to the negative x squared dx, and I'll add that to the other half, if you will, of the integral. I'll introduce the letter b, and I'll make b head toward infinity. So set up a limit for each piece of this integral. And now to start finding the antiderivative, I'm going to use a u substitution. Keep your limit in your work. I'm going to write the antiderivative. I'm going to bring x back in as my variable. Notice how I'll bring the appropriate limits back now as well. I didn't draw them in my work when I was in U world, but when I came back to X world, I brought the limits that apply to X. I'm going to evaluate now. When I take the limit now, as a approaches negative infinity, I don't need to do anything with the first term. The first term is actually 1/2 times 1, so I get negative 1/2 for the first term. And then look at infinity in the second term. That e is to a negative power. That means it's actually in the denominator. So that's 1/2 times e to a very high power. So infinity is going in for a, or a big number is going in for a. That means that term is going to 0. On the second limit, the same thing is true in the first term. E is to a negative b squared power. That means e to the b squared is in the denominator. And if b becomes a very, very large number, then that term goes to 0. The last term is the same thing as 1/2 times 1, so that's plus 1/2. Negative 1/2 plus 1/2 is 0. The value of this is 0, and that means the integral is convergent. Here is a tip for you also. If you have to break up a type 1 integral because it has negative infinity as the lower bound and positive infinity as the upper bound, when you go to set up the two, you have to set them both up in the first line, but you can work the first one out first. You don't have to work out both of them at the beginning. If the first one works out and you get a value like we did here, then you know you have to go back and work out the second one. But if the first one works out and you get infinity as your answer, then that makes the entire original integral divergent. So you would not have to go through the work of figuring out the second limit. Now it's time to try some on your own. So we have 5 problems here from the section for you to try.